Have you ever wondered what's actually in the stuff you use every day? Well, today we're going to put on our detective hats and explore a classic chemistry technique that answers a really simple question: what's inside, and more importantly, how much? We're talking about gravimetric analysis.
Think about it. Take a simple painkiller. You trust that it's going to work. But how does the company that makes it prove that the exact right amount of the active ingredient, say paracetamol, is in every single pill? Well, it all comes down to this surprisingly elegant art of precision weighing. All right, so here's our roadmap for this little chemical detective story. First, we'll set up the case, that dose in your medicine. Then we'll need our primary tool for weighing something that's basically invisible. We'll see how it takes us from a chemical soup to a pure solid. And of course, every good story has a villain, so we'll uncover the problem of unwanted guests, see how chemists clean up the evidence, and finally wrap up with why all this precision really matters. Okay, so our case file opens with that pill. It's not just pure paracetamol, right? It's a whole mix of things. You've got the active ingredient, but you've also got binders and fillers that hold the tablet together. So our challenge is to figure out the exact amount of that one active ingredient and completely ignore everything else. And that right there is our core mission. We have to somehow pull out our one target substance from this complicated mixture and weigh it with incredible accuracy. And this isn't just for medicine. It's how scientists check for pollutants in our water, or how food companies verify what's on the nutrition label. And lucky for us, there's a classic, time-tested method to do exactly that. So the solution is a technique called gravimetric analysis. You could think of it as our chemical detective's most reliable and trusted tool for this kind of investigation. And really, it's all about making the invisible visible and, more importantly, weighable. At its heart, gravimetric analysis is actually beautiful in its simplicity. You take the thing you want to measure, what a chemist would call the analyte, which is dissolved in some liquid, and you basically force it to become a pure solid. Once it's a solid that you can physically hold and separate, well, then you can weigh it. And that final weight tells you exactly how much of it you started with. It's brilliant. The logic here is just rock solid. First, you trigger a very specific chemical reaction that makes only your target turn into a solid. That process is called precipitation. Then you just have to carefully separate that solid from everything else. And finally, you try it completely and weigh it. That final, pure mass, that's the key. That unlocks the answer to how much was in there in the first place. So what does this actually look like in a real lab? Let's walk through the whole process. We're going to condense the full lab procedure down into 4 main stages that take us all the way from a messy liquid soup to a pure, weighable solid. So as you can see, each step here is super meticulous. It all kicks off with precipitation. You add a special chemical, a reagent, that reacts only with your target to make it a solid. Then comes digestion. And no, we're not talking about lunch. This is where you gently heat the mixture, which actually lets smaller, imperfect crystals dissolve and then reform onto the bigger, more perfect ones. Kind of cool, right? Next, you filter and wash everything really thoroughly. And finally, you stick it in a special oven to get rid of every last molecule of water before you weigh the final, pure product. But, just like in any good detective story, there's always a complication. The process isn't always perfect. Sometimes, other chemicals from the original mix decide to crash the party. They get trapped in our solid, and that threatens the accuracy of our final weight. This quote just nails the problem, doesn't it? If these unwanted guests get mixed in with our target, our final weight's going to be wrong. It'll be too high, making us think there's more of our substance than there actually is. And in the world of medicine or environmental testing, that's not just a small error. That can be a really big deal. Now, these impurities can sneak in 2 main ways. The most common one is called co-precipitation. This is where the impurity gets trapped inside your solid as it's forming. It's like an accomplice getting caught up in the main event. The other way is post-precipitation, which is when an impurity decides to form its own layer on top of your target solid after the fact. And if we look closer at co-precipitation, you can see there are a few different ways these unwanted guests can hide. Surface adsorption is the simplest. Impurities just kind of stick to the outside. Mixed crystal formation is way sneakier. Here, an impurity that's a similar size and shape can actually take the place of one of your target ions right inside the crystal. Then you have occlusion and mechanical entrapment, which is basically where pockets of liquid get physically trapped inside the crystals as they grow, especially if the whole process happens way too fast. Okay, so we've got a problem. But don't worry, our chemical detectives are clever.
They have a whole toolkit of techniques to deal with these unwanted guests and make sure the final evidence, our solid precipitate, is as pure as it can possibly be.
So that's the million-dollar question, isn't it? How do you fight back against these microscopic contaminants to get a truly accurate result? Well, they fight back with some really smart strategies. Remember that digestion step? Letting the solid stew in the hot solution gives the crystals time to sort of perfect themselves, kicking out trapped impurities. Meticulous washing and forming the solid nice and slow also helps prevent things from sticking to the surface or getting trapped. And for the really tough cases, there's the ultimate do-over, reprecipitation. You literally dissolve the whole thing and start again, which leaves almost all of the impurities behind. So we've seen the crime, the investigation, the forensic techniques, the whole shebang. But let's bring it all back to the beginning. Why does all this incredibly careful, meticulous work matter so much? Because this isn't just some academic exercise. The stakes are really, really high. So let's say, after a perfect procedure, we find that the true weight of the paracetamol in our pill is exactly 1 gram. This is our baseline. This is the correct answer. But what if our process was a little sloppy? What if co-precipitation happened? Our final weight might come out to 1.0250 grams. Now, that extra weight isn't our target. It's the impurities, those unwanted guests. And that might not seem like a big difference, but in the world of science and medicine, trust me, that is a huge error. And that right there is the crucial takeaway. That tiny error, when you multiply it across millions of pills, could lead to incorrect dosages. In environmental science, it could mean you're misreporting the level of a pollutant in a water sample. It is literally the difference between a product passing or failing quality control. This level of precision is the absolute bedrock of reliability. It really makes you stop and think, doesn't it? In a world that so often runs on good enough, it's a powerful reminder of all the hidden science that demands perfection. From the medicine we take to the environment we live in, this fundamental technique ensures that what we know isn't just an estimate. It's the truth.